So, in continuation to our discussion on applications of image processing, we have considered one suitable application as one in agro sector, and the problem is classification of rice fractions in the grains that we receive on public distribution system. So, FCI is a procurement agency and storage agency, and there are other marketing agencies like Markfed and other state agencies. So, BIS, Bureau of Indian Standards, has already generated long ago a standard for such refractions in the grain, in the rice grains. So, without going to details of this that will follow in the case study, I am here to just give you some important points of the title. The title talks about uniform specification. So, uniform specification, here I mean that it is no longer a subjective way of choosing or binning the grains. It should be like uniform on a national basis. So, it is not that you find labor doing this job of binning the grains and finding the good ones in one place and other refractions, whether they are broken or colored or discolored. As you will see the details, there are 10 kind of such refractions. So, we are going to do rice, just the same rice, into 10 classes. So, the normal grain that we receive through public distribution has lot problems or refractions as they call it, which are undesirable in nature, but permissible in certain limits. So, the application tries to know the properties of grains, each grain, tries to classify them through color image processing, and also gives them a report like a certificate, like an online report. The online version is also ready now, after all that color image processing and classification. So, the uniformity point was when I mentioned when totally automation is achieved by a machine on a 24/7 basis. You will see later on a version, online version of this is also possible, where a submission of rice grain sample is done over the web. So, the idea is that uniformity can come over a large sized nation as ours without getting subjective classification of this. So, that is the basis of all that in the title that I picked up the word, say, uniform specification, like a standard basically. The uniform specification comes from the standard. So, giving you now this case study in somewhat details and skipping the fundamentals that we have already discussed on color image processing. This now slide gives you the objectives, the other approaches available for similar kind of applications, the algorithm that we have developed in the form of a flow chart, and how humans have been doing in the past classification of grains through visual means or through manual means or even through algorithms in some limited manner, and applying it to the total grain level, finally using training of artificial neural network for classification of such a application project, and also making some comparisons of other approaches. And ultimately, as I mentioned, the agro sector has come from social sector and it has a social impact. The uniformity word, which I discussed a little bit earlier, creates that social impact as well. So, with that summary, we move ahead with some objectives. So, as you can see, the work is to see that the refractions, some of these details may come from application, as you will see. So, please bear with me that there are some of the domain knowledge that we had to acquire and anyone working in an application would have to acquire. So, some of the information may appear somewhat unrelated to the image processing, but actually the problem wise we had to go through all that. So, if I say, when I say fair average quality, means acceptable quality of refractions, acceptable quantity of refractions, basically they have specified in percentages, like how much of percentage is acceptable. So, by weight we have to measure it quantitatively at the end of the report generation. So, we have to know how many of the grains are undesirable refractions for each class and then weigh them. Again you will see weight has also been obtained through software simulation, that training has been done within the system. So, and also with that relaxed specification is a term used by BIS, that there are some relaxed specification, means the percentages values are specified in a relaxed manner, that okay, certain number of say broken grains are allowed, some percentage of grains are allowed. So, that way it gives as relaxation, because this grains, these grains that we have are not expected to be 100% sound grains. So, some percentage of say certain refractions are allowed as acceptable, that is the term. So, coming to the now technical details, except the first objective was to use flat bed scanner. The imaging acquisition system here is that way, a flat bed scanner which is a common office scanner. So, the imaging sensor in this case, you would see instead of using a camera or any other, we have chosen to use this way, just because I mentioned the application of online web kind of service was in our mind, that therefore, we have not used any dedicated any special hardware, but a dedicated rather than a dedicated hardware, we have used an available kind of office scanner. So, that is the idea, that so that the advantage of available equipment can be obtained. So, as a byproduct, I have already mentioned that the process of milling, if you see the industry behind it, those who are milling can know in advance, a lot of transparency in the judgment can be made. You may not know, but there are sometimes allegations that the subjective evaluation of a particular sample may not be reliable, may not be done in a transparent manner. So, with the machine available in use, the transparency and reliable accuracy etcetera are the objectives that as a byproduct. So, now coming to those 10 refractions. Now, look at it, the rice grain is not just simple white or nearly grey kind of grain, it has so many refractions, as you can see. Some of them are inorganic, which are not desirable, except the sound that is given here as a second. The sound grains are the real good grains that we are looking for. Then on the sound grain itself, there are categories because of their geometry, loss of geometry, they get broken due to milling process, and there are some of them are so broken that they are called small broken, and some of them nearly approaching the powder size called organic matter. Organic matter in the sense they are nearly powder like, very small sized, but they are still edible in the sense that they are part of the grains. Then there are undesirable, see some of you who have the background might know that there are red grains. See the red grains, there are some red peels available on the skin, and they are not fully milled, and this is also not just limited to milling, this is also due to the growth of the grain as well, as per our knowledge. Sometimes due to wetness and other humidity, there is a discoloring, and that is also shown as discolored. The chalky behavior here is like a chalk, the grain acting as chalk rather than a translucent, edible, nice, healthy grain. Sometimes they are damaged due to the growth process or through the milling process, and admixtures are the grains which are not desirable, but they are also edible, but they are not in the level of quality that is expected in the grain distribution. So, we have a problem like that, where grain is no longer a simple grain, but there are 10 kinds of refractions in it, which are only one of them is desirable. It is like that kind of classification problem. So, we start with the processing and reach the classification level through intelligence, as I mentioned, the training of neural network also incorporated in the application. Now, of course, showing you the way the system works, some little bit of ingenuity everywhere. Now, see the scanner and see what we have done with it. We have added a small background of black color to maintain the thresholding operation perfectly workable. Now, thresholding, we know why it will work and where it will work, we have studied it, we know the limitations of it. We have added a black layer, assuming that the grain will not have any similarity of this blackness. So, we have simply put a black layer, and what you cannot see is a transparent layer also lying on the glass of the scanner, which gives us security of the scanner and safety of the scanner. While using the scanner, if you keep putting a lot number of grains again and again, the scanner surface will get damaged. So, it is a part of disposable small kind of, you can say, like a file cover with one side transparent, the other side as black, and the transparent side lying on the transparent glass, and the sample can be put on that. So, this is what we are doing as simple imaging using the available office scanner with a slight change on the sampling process, not the sampling process, but the sampling imaging part of it when the sample is being imaged. So, there is a sense at every place, and if you lose it, you do not gain it after the step is over. So, this was something to allow, now you can imagine this was to allow thresholding to work properly. This is a small you can say change to the system. Now, what are the other approaches? Those of you who might have know, as I already mentioned, for other objects of agro sector, the scanner may not be applicable, say for pumpkins. Somebody will say if we were to do watermelons cannot be put on the scanner. So, normally or any other fruit cannot be put on the scanner, only grains and seeds like kind of objects can be put on that, products can be put. So, other approaches use as I mentioned 3 CCD cameras are available, which are true color 3 CCDs, not just one charge coupled device, it has basically 3 cameras in one. Most cameras do not have total true color kind of acquisition. The 3 CCDs are meant primarily for one color, say red, green and blue. In this case, there are color infrared cameras also, which have 3 bands excluding the red, but including the infrared, which is generally helpful for the skin depth sensing of fruits and vegetables. So, there are other applications using 3 CCD cameras as well, and other work on this has been using only grayscale imaging also, which did not consider the color aspects as I mentioned. Their purpose was only to see the level of you can say brokenness in the grains. So, if you were to do only thresholding, make geometrical dimension measurement, then only grayscale imaging would have been sufficient. But you see the colors used in the refractions, and even in other colors which may appear chalky or discolored as almost all gray, but the color information was required to separate from the sound. Even the sound grain has color element in it, though it appears to be translucent or gray color, but the shades available in the grains required overall color image processing. So, we chosen that way, and as I mentioned here, very few systems have taken refractions in the larger number as we have taken, and some have limited to 4 or 5. In this case, we have combined all sort of refractions as per the standard. Then some satisfactory performance has been reported on even brown rice, which is not gray, which is brown rice. If you know, you do not know, maybe in India we do not use that. So, brown rice is also a category, people have worked on that as well. Now, considering the algorithm in nutshell first, and then taking the steps one by one. Now, the scanner, if you use any time, will acquire a true color image of a document or a sample, in our case say rice sample. So, we can get a true color, that is 24 bit 3 colors per image per pixel kind of image is available using the flat bed scanner, and you may be surprised why we have chosen. One reason we had told you was the availability, easy availability of flat bed scanner, and the other is that the quality of imaging for a grain like situation using a flat bed scanner is much superior than any other camera method, because it is in close contact with the sensor. So, you can imagine the documents are scanned because of their planar 2-dimensional nature on the flat bed scanner, not by cameras and other things, and scanners are slower than cameras, but the quality is higher because of the uniformity of illumination, close packed kind of situation and close contact kind of imaging. So, you find far repeatability available using scanners of this kind, that is flat bed scanner. So, now somebody might have imagined that when you place rice sample, grains may be touching each other. So, it is not just thresholding would or any other segmentation will keep every grain separate, many of the grains may be touching each other. So, there is an algorithm called water shedding, which separates the closely touching grains from each other. So, water shedding was also required, of course, after the binarization process which we discussed earlier using thresholding. So, that comes next. Now, and that situation once water shedding has been done, the grains have been separated into say a binary image, each one having an index. Index means the number associated with it. We may consider, we could consider their geometrical measurements as to what is the length, what is the breadth, what are the other parameters. So, you will see all those parameters they are mentioned here. For example, size dimensions are length and breadth, shape dimensions are projected area, perimeter, convex perimeter, compactness, roughness and elongation. You will see that some of them are basic parameters like length, breadth and area, even perimeter. Convex perimeter is another parameter. I will come to these parameters once again later on, and then there are some derived parameters also, like for a compactness you can divide one dimension with the other. So, perimeter over area can be used as compactness. So, the idea is that even roughness has been shown here. Roughness is like you make a rough measurement say through a thread. Suppose you want to measure a perimeter of a chair, you may just run over a thread and make that length measurement as a rough measurement, and then have a proper perimeter measurement through pixel by pixel level measurement. So, the ratio of the two is considered as roughness. The object which is circular will have same dimension as 1, and any object which is non circular will have roughness indicated as non 1, value different from 1. So, we will come to these details of these steps also once again, but at the moment the whole algorithm is given in nutshell with the next step as color segmentation now. Though we said binary, we may have chosen one of the shades say from red, green, blue or even HSI as we mentioned. At some stage as I mentioned we will enter into HSI model also, but as such for the steps till now till the binarization we could use one of the colors, and red, green, blue or green could have been used. In this case we have chosen red as the appropriate color for binarization process. Due to the involvement of red in other defects we had chosen red image as the, because geometry could be measured by any one of these, but we had to choose one appropriate, isn't it, because it is quite possible that the boundary obtained by red and green and blue may be different because of the non presence of say blue color, or not that it is not present, in a gray color all the colors are present, but the dimensions are better obtained by red. So, we chosen red color as the base for binarization process. With that as background now, what we have done in the next step as you see color segmentation, we have copied that model to all the three. So, the segmentation in red, green, blue all three is obtained. So, if it is becoming too descriptive all the visuals will be visible. So, just for the sake of completeness you can say a summary of the algorithm is given here as step by step process. So, in that process we get red, green, blue images of each grain. In that process since water shedding has been done, each grain image is also separated from the overall big image which contains large number of grains as you saw while we were placing the sample. So, then comes the RGB to HSI or HSV model conversion to suit the reasons as we mentioned we do not process RGB, we process HSI or HSV. So, then comes the classification problem where we use methods of pixel classification first. Pixel classification means each pixel on a grain is classified to be red, chalky, discolored or all the refractions that we mentioned which are related with color, and then we do the grain wise classification later on. So, first we do on a smaller micro scale level where each pixel is first classified. It is like for a skin classification of a person we might say not RGB, what is the pixel on a skin of a person, we say fairer or say darker or blacker, isn't it. That way we do the same thing on pixel classification of grains as well. You will see again the details. Then we come to a grain level overall classification that okay, the grain has some red in it, some discolored in it, some chalkiness in it, some percentage of say soundness in it and some kind of damagedness also in it, but still the grain is okay, because these percentages are small, the soundness percentage is say good number. So, some training of the system has been done. We are concentrating here on neural network application, but rule based approach has also been done, and now fuzzy rule applications also we are trying. So, what I am trying to say that a grain level classification is the last level classification that is obtained before the report generation. So, with that grain wise report, then we are able to classify each grain, and we have a model generated that gives us some density values. Like we know that this area of chalky will generate this much of weightage. If some of you who know, when you put grains in water, the lighter ones will come up, is not it? The chalky ones will come up. Why? Because the chalky grains are lighter. So, what we have done, we have taken a large sample of chalky, all refractions, and measured them by weight. So, we had a good samples acquired from Marquardt, both for classification purpose and also for training of the density generation. So, from area, not volume, because it is a two dimensional process that we are doing. From the projected area of each class, we could get the particular weight wise report also after we had obtained the number wise report. So, this gives a sort of brief overview of the algorithm, and now again some diagram can probably clarify better, wherein steps are given in the form of blocks. So, as a process or as a flow chart, we have a scan or load kind of step in the first instance. We get a rice sample image, and we may also store it as a database if required. All good samples are stored in the reference database as well. The processing is done by smoothing, as I mentioned, red, by averaging filter that I mentioned, all ones in a mask of convolution matrix, that gives us readiness for thresholding. Many of you may say, as I said, smoothness is still required before you apply threshold. If you do not apply the smoothing operation before threshold, you will not get good boundaries. So, these are the restoration processes that we are doing, which are not visible, which are not even appreciated in the beginning. Somebody might say the image is good enough, straight away why not threshold it. So, when we smoothen it, the histogram becomes very smooth, the class of background and the grains become clearer, and the separation by thresholding value chosen by us, again automatically the system automatically gets that value point in the histogram, is easier, is rather reliable. So, that gives us the binarization, and then a water shedding algorithm, which whose detail I am not giving, is able to separate the grains which are touching each other. So, parallelly then once we have readiness for geometrical measurement, on the right hand side we get each grain, as I already mentioned, into color segments. Each grain gets segmented into red, green, blue kind of. So, when we start, we have say 400 to 500 grains on the image. We segment them, each grain gets separate image. So, cut kind of image that we call it is available for each grain, and then we have 8 geometrical parameters which are mentioned here, already discussed, and there are 5 color parameters which are straightway coming from the classes of interest, but this is at a pixel level. These measurements are done, the two are combined together, a statistical analysis is done to see on what ranges each one of these lie, and then rules are made on one side and a training of neural network is done on the other side. So, basically we have two approaches here available with us, and then either of them can be used, and there are advantages and disadvantages of both of them. You will find the comparison of these as well, and a report is generated as a kind of certificate. It is like marks obtained by a class. It is a total class report, which with each grain parameters are also available as a report. So, again as a block diagram, this sample image onwards, probably things will become clearer of what I have been trying to say. Now, this shows the sample with lot number of grains, not very nicely decorated with, you can say, special care, but reasonable care that at least they are not just bunch of, not a large bunch of grains at one place or not overriding the other at one place. So, but they are also touching each other or closely, and there are situations where water shedding also does not work very well. So, it is not that once we have water shedding or any algorithm that will solve each problem, every problem here. So, sometimes if you see some situation, you will find the grains are so parallelly touching each other that they appear to be one. So, the algorithm may not find separation of these. So, this is a sort of natural distribution with some reasonable care, and a sample image is visible here. Now, this shows only the histogram analysis that goes in the background. Initially, we had it in a manual mode. Now, it is just to show you that histogram like that is available. The histogram is smooth if you have smoothened the image. This is a very simple observation. If you have smoothened, means you have reduced the variations in the image, though they are appealing nice in the beginning, but for a machine to use thresholding, it is required that you use a simple 3 by 3 averaging smoothing filter. So, that gives you the smoothened kind of histogram as well, and you can see the two peaks indicating here, one of them as background, and the lower one, the smaller one is actually the grains, because there is a lot of black in the image. So, the first peak comes as black background, and then there are grains with some heap, some peak here. You can see that second peak, and also which is not visible is the third peak here is also a chalky behavior, that is too bright, too white, undesirable, but it is there in some of the grains. So, a small portion of pixels do contribute on chalkiness as well. So, we choose a value somewhere in between the first two valleys, first two peaks, and find a valley, and the system automatically finds the center of the two and gets a particular threshold automatically selected, and the grains are available as such. Now, you can see the whole image processing follows reverse of engineering. In natural products, we do not design the rice or we do not create the grains dimensions and all that the way we do in engineering. It is the other way around, we actually measure them through this process. So, this black and white is something like black and white drawing, you can say, but at the moment this aspect of the image has lost all the colors. So, this is, as I said, only red color segmented as binary image for dimensional measurements. The color measurements are done separately. So, this becomes the basis for color segmentation afterwards. This is the first step, you can say. No, we do not do anything on equalization, no way, never. It is very nice on enhancement, but we do not do equalization. Equalization is required to improve the appearance.
Then taking the histogram
We take as it is.
What was done with that
Histogram gives us the value calculation of threshold. In a way, histogram gives us a feeling of where they lie, what statistical distribution they carry on background as well as grain. So, that way gives us a middle point. We safely take a middle path, keeping the rice grains on one side, background on the one side and the rice grains on the other side, and you can see this now. It is a perfect black, jet black with jet white, not jet white, I do not know what you call it as perfect white. So, it is a two color image now, binarized. So, this is where we can make the dimensional measurements. Now, see, now it is very much like putting rice grains on the drawing board. That is where I mentioned reverse engineering. We are not producing grains by engineering, but we are measuring them for their quality and dimensions. So, in this case they appear as if we have acquired them on the drawing board, and every grain's center, every grain's boundary box has been obtained, and as you can see the indexing has also been done. The numbers are visible, I do not know if you can see, the numbers are visible, and some of them still closely not leaving the friends position, they are very close, tightly coupled with each other. Some of them are, you can see there number 3 here, they are 2 together. Well, I do not know whether this image is shown later on for water shedding, but the effect of water shedding will separate the images, separate the grains which are very closely touching each other. So, in the grains also we do not want them to be in this manner of socialization, you can say. So, going ahead with this is called blob analysis. By the way, the title blob analysis is binary large object. Though in this case the gray image is shown, one of the gray images, say red color image, it has been shown, but it has been obtained through the process that I mentioned just before, that was binarization. So, that image has been used to index the grains, to make the dimensions, the parameters you will see in a report, full report, all grains dimensions, it is like index wise, like a class report in roll number wise, and then dimensions are available apart from the color parameters that are kept separately. So, we are talking about the monochrome color based dimension measurement first. So, this shows the indexing and labeling as well. Labeling is indexing are the same thing. That means, they have been labeled that at this place grain number 1 is lying, at this place grain number 2 is lying. So, each position has been marked inside the table.
So this blob analysis, I am not aware of it, but is this facility there in image processing toolbox of MATLAB?
No way, the whole project is not using MATLAB. MATLAB studies were done in the beginning for say color feature extraction, some rules adjustment for values, which values range analysis as we call it. It is like for what ranges the red grains are lying. So, just computing the histograms on red, green and blue, those HSI that I will come now. To see those dimensions, to see those statistics, only these were used, but MATLAB cannot generate a project of this kind. Now comes the question of which tool. Now, we have what we call a library of Matrox imaging library, MIL. That is a development tool. You will find that lot of development tools are used in this. So, the development tool is MIL, Matrox imaging library, that gives us the process of blob analysis, this process. So, blob analysis means binary large object, all large objects of binary nature are counted for their indexing as well as their dimensions and geometrical measurements. So, there is a list of parameters, you can choose which one you want, the library, and then use the functions as dynamically linkable library, DLLs. So, the project gets integrated with it and we get the outcome as this. Now, the water shedding, as I mentioned, the grains here are showing the whole image now. Now, though closely you may not see, now the enhanced version of the image is visible, not enhanced, sorry, enlarged version, the full view. This is actually the full view. Now, you can imagine a camera cannot generate a 300 dots per inch resolution on an A4 kind of image so easily with this quality. Now, this is something like 3000 by 2500 kind of. So, it is a 6 megapixel or more than that image that we are acquiring in each go, and it takes a sort of few seconds to acquire the image. As you know, the scanner's movement is not as fast as camera click. So, this is how it is. Now, in this case, this shows the effect of water shedding. Then there are other effects here. This also shows sometimes wrongly, this could not separate here rightly, but it has separated wrongly. This could not be separated. Now, this might be even wrongly separated. So, water shedding also may not be perfect. It may be doing, if the parameters are not chosen appropriately, or if the sample is not appropriately placed. As you can see, the two grains here joined almost parallelly with each other, you cannot assume them separate. The algorithm cannot find them. I am not giving you again details of this. The details is simply that if there are two centers emerging, like a cell, cell breaking up, it is like if a cell is breaking up, if they find that there are two centers that one could locate through statistical approach, then the algorithm tries to make a cut in between. An axial cut is found that okay, it seems that two objects are joined, like naturally you find bananas are available as two, sometime naturally they are grown together, sometime mangoes and all. So, you find that actually they are twins kind of situation. they have just got coupled naturally, and their centers could be thought of imaginarily. Same way in this case, it is assumed that the objects are just close, but their original centers are different. If you can think of an algorithm, well, the details I can give you later on, then it tries to actually separate them, make an orthogonal cut in between, and then separation is possible. But sometimes there could be a wrong estimation also.
Sir, in this situation, it will give wrong classification at least.
Yes, it will give wrong classification. Yes, anything we are doing, if you are not maintaining the truth while searching for truth, yes, the end result is bad result. It may be that finally we get some error in that particularly, say, if we wrongly cut in between, the dimensions may be wrongly placed, or a particular grain may be, now this will be shown as one grain, which will have a double dimension. Now, the advantage with the other parameters availability is that through some other post processing, we may know that how a grain can be so thick. So, if you find the dimension of this grain, we can remove them from analysis. So, there is some segregation possible at a later stage due to the oversized dimensions. Say a particular grain is going too long because the grain got joined with it. So, some level of separation is segregation is possible as post processing, but some level of is still not possible. As you can see, if the grain is broken by this algorithm as here, I do not know if it is rightly or maybe wrongly cut, or if there is an error here, as you can see, then probably the dimension might be wrongly calculated, or any error can occur due to this chopping behavior. So, it is up to us, or ask the person to place each grain slowly, each grain not touching each other. It will take more time, either you take more time or algorithm would take more time with some error, some objectivity, some error. So, some allowed percentage of error has to be there because of the level of carefulness, the way the sample is placed, or one could think of improvement in that as well.
By using the major axis and minor axis
Mm-hmm.
the grains, we can very easily detect that there are some of the grains are to be rejected.
Yes, yes, no, but the dimensions are indicating of what can be rejected. Post processing can give some of them, not all of them. As I said, if there is a cut here, you will not know that the length was wrongly calculated. So, it may appear as broken, it will be classified as broken while actually it is not broken, and this grain will unnecessarily have more area in calculation and may find difficulty in classification. So, some of the errors, as I said, can be processed as a post process correction, some of them cannot be done. It is like you have a spell checker, you may have some spelling correction, but some of, if you do to so much of bad typing that even spell checker cannot do it. So, it is a post processing is similar to that, like spell checker post processing. Some of these can be taken care of, some of them still cannot be taken care of. So, there is there is always a kind of risk involved in it. Now giving you the labeled kernel image, the labeled kernel image here again shows what I said earlier. Now, here you can see each grain has been watershed. Now, it is showing you the outcome on the original image. Actually, the processing is done on a binary image. So, many times you find the labeling, the say putting a box, putting an index is differently done. It is a layer on the original image. It is just to show on the original image, these boxes have been drawn on the original image. The processing is not done now, the original image has been processed and binary image is being used. So, this blob analysis gives you that, and watersheding still could not do this, as you can see. So, in this case some of them may still remain joined and may continue to remain, say, a long grain which you know that naturally is not possible. So, a prior knowledge can help you there as post processing. Now comes the training aspect. I think I have taken color. Okay, giving you some color attributes. I think details of color have not come here in the visible. Just to give you that these boxes which were indicative here can generate different each grain's images separately. It is up to you, we chose to separate them, we could have kept them together also, since we knew their placement. We have actually separated each image and taken background also. Now, you can see in some of the, in this case for example, the box for 254 is also shared by 260. So, we had made an arrangement wherein we can remove the encroachment by the other grain. So, each grain was separated for its color classification separately. So, like in this grain say in this sample say 400 grains were available. So, each image gets separated as 400 images, 400 red images, 400 green images, 400 blue images of the original sample, and then comes HSI, which I mentioned earlier. So, I think the color image processing details are not given here as visuals, then each HSI each RGB is converted into HSI by the model that we discussed earlier. So, we convert RGB to HSI for each cut image, as we call it, each grain is separated and we know the index of that. That is where the color dimensions are obtained, colored features are obtained.
Sir, can you please explain again what is blob analysis?
Blob analysis is given a binary large object in a background of black and object as white. The analysis generates through a scanned process left to right, top to bottom, keeps counting the objects, keep noting down their boundary element, because they are object means they are separated already, assuming water shedding if required has already been done. So, it keeps a bins of sort of array generation, wherein it notes down, okay, this is object 1, object 2, whenever the new object arises it adds to the object, whenever the old object finishes, because in a new line a particular object may be finishing, losing the boundary and a new object starting off. So, accordingly at the end of the scan you come to know the number of objects, you come to know the area within that, you come to know their coordinates. When each coordinates are available you can find the boundary, you can find the perimeter, there are algorithms to find length, as he said major minor axis generation. So, major axis, minor axis, length, breadth are measured, and these are the geometrical analysis, simple geometrical analysis is possible through blob analysis. So, it has a set of, most libraries in the development mode gives you blob analysis and a set of physical projected area kind of parameters are possible to be measured for anything that you place on the background. If it is black, if the thresholding has been done, blob analysis will generate you the list. So, that is one go kind of process available, and Excel sheet kind of processing is possible. Array results are, I mean the details of developments are you can say once you are in the field you know them, how to handle them. So, a sort of Excel sheet gets generated, as you will see later on. So, we will see somewhere the Excel sheet also visible here. The system has to be trained now, it is not end of it. Even with all that measurements, I do not know whether those details are of your interest or not, but just for sake of completeness I am telling you, the system needs to know the training of the dimensions given and the pixel classification done for each grain level, and then the percentages of scores we call them obtained for each grain as grain classification. So, I think if I list them then it will be easier, but to give you feel of training, that I will come to details also. The training means either you apply rules, you are, if you are an expert you know if this is this percentage, say if the grain is say 80% sound pixels are there and say 1% red pixels are there, 5% chalky behavior is there, or some other whatever rest is say discolored, what will you call it? Who will tell us? If you ask the expert they will say, I do not know how you have done the earlier classification, you are saying that this much of red, this much of that, I only know that if there is little bit of red you must classify it as red grain. They go like that, isn't it? So, the way we have done the first stage they do not know. So, that classification was ours, we just took some analysis and found that they are calling certain grains as red, they are calling certain grains as chalky, we have just put them together, we made a personal. So, there is a lot of personal observation or statistical observation required to make a range analysis. Then we know that all red grains lie on this say range of H, on this range of S, and then reach this range of I. So, HSI model is there, but that gives us only pixel classification. Then after that I know a grain has some red pixels in it, as I said in terms of percentage. Again that range analysis was required to classify a particular grain, isn't it? I sometimes give an example, if a person has stolen once, we call him a thief, because he is otherwise okay, but there is one case of theft with the criminal. Similarly, if they one, I do not know what percentage of red say required to call a to a grain as red. So, red is something like a criminal kind of as they say it is very poisonous or not really good for health. So, but still some percentage of redness is allowed to a smaller extent. Now, they have given us just samples, we have taken them for training. Initially first we train ourselves, then we generate some data to rule, and then the pixel classification was done by our own analysis. The other classification can be done by rules. Range analysis for rules was easier on the second stage, or otherwise we put all the samples in the neural network and label them. We know that they have labeled us, particularly this measurement has generated the grain as red, this as sound. So, we had some of 5 to 6,000, 7,000 grains with us, where each grain was labeled by them, and we knew that this grain is labeled as this particular class for training of the system. And also, as I said, they were also used for weight calculation. I think the diagram here will give you better feeling. So, we considering all the grains, say many of them were sound, big broken and small broken, chalky, all these grains had different density. You can see though grains are all small broken or big broken or sound, they are all the same grains, but why they are broken? Because their density was different, and why they were broken is it is basically there is a linkage of brokenness with the density as well, and chalkies are very light. So, this is the kind of calculation. We knew that a set of say 420 chalky grains were weighing this much, and we knew the area that we had calculated through blob analysis. So, linking the blob area with the weight available, in a way our density is gram per millimeter square rather than volume, because we are not actually measuring the volume. So, this could be another limitation somebody might assume. We are not actually seeing things in 3 dimension, it is actually a 2 dimensional analysis of a projected image. So, in that situation you will find the discolored ones are the heaviest ones. Red grains are also very heavy, is not it, though we had very small number of red grains available with us. So, like that the idea is that they are also part of the reporting, though it may not be appealing to you for academic point of view, but as a problem solving, because they want report in terms of weight, they do not want in number. So, going ahead, now this is that range analysis I was mentioning. The color now the color feature extraction is explained here. These are now quantified rules. These are obtained initially by observation. Herein we can also play some fuzziness if required, but this is at a pixel level. That means, if HSI or HSV as the name here is in the range say 7 to 25 degree H, 0.2 to 0.45 S, 0.6 to 0.9 V, a particular pixel with this range is considered red. And now comes the then discolor is again you will find even 7 to 25 is buried in the discolor as well. There is a lot of overlapping, underlapping, well no underlapping, but there is some overlapping in a particular parameter. This table you can imagine takes a lot of time to generate.
Purpose we have taken only gram per mm square as the
Yes,
parameter.
yes, that is training of weight part, not the class will come now. That is only for measurement of weight from the area to weight calculation. Initially we have modeled, it is like taking certain chalky ones and see that okay these many chalky.
How many parameters by the way has been taken for the training?
The numbers are given, parameters are
Like
5 and 8.
density is there, then the others are
Density is what we are calling it.
just one of the parameters.
No, density is not there, density we are generating
Okay, no
for area to weight kind of ratio.
gram per mm square is so
That is our name to it.
what second, third and fourth what are those?
No, there are 8 parameters,
8 parameters.
8 geometrical parameters and 5 color parameters. Now, these are 5, 8 if you want to recall,
Those are those that will be coming now.
no these were given here also they will come.
This.
These are geometrical attributes are rule based analysis does not use many. If I will see, let me see where we have listed. I have listed them already here. See here length, breadth, area, perimeter, as I said, and convex perimeter is the rough kind of fast kind of convex perimeter. Convex means the perimeter which maintains convexity, not taking the depth of say concavity,
Not concavity only.
just taking a roundness in it. But if there is concavity, then you must take that.
Is not taken.
Concavity will come when there is a proper perimeter will have concavity. That is to take care of roughness. That means roughness will ignore the concavity in the first instance, but actual perimeter will take it. So, the ratio will give us the roughness. That means the object was having roughness in it. If the two perimeters are not same, that means the object was not convex. It was having some depths in it which were ignored. Non-circularity. So, these are the 8 geometrical parameters and there are 5 color parameters. Now, we are talking about 5 color parameters after this density modeling. This we can call it modeling. This was modeling in the sense we took some weight, we knew some area through our image analysis. See, like our image analysis goes in the computer, that gives us area. The reality says this is the weightage, we have to relate that, we have to relate with the reality. This is our density value. Now, this is our observation on the HSV model. Values were obtained through HSV model available say in MATLAB or implemented in, we implemented the same model in the project in the whole application. So, we converted RGB to HSV and then found these say classes, looking at closely each red grain, each discolored grain, each chalky, maybe manually or you could have a statistical analysis. We had a statistical also, all reds were histogram, all histograms of H, S and V were taken, and then we found that red ones are lying in this, and you will see that this segmentation say 7 to 25 only in red and why not somewhere else. This was again manual classification. It is our thinking that okay, let us cut it short. Most of the say red ones are having 7 to 25 of H, okay, and their S values are 0.2 to 0.45 and V values are 0.6 to 0.9. This is kind of observation.
These are the opinion of the experts, we can say.
No expert. These are image processing experts. They do not know what is HSV. You ask them, they will say what is HSV? We do not know. That is the problem. That is where the problem comes. You say the expert knows nothing about the subject. You know nothing about the domain.
No,
There are two experts.
when I am saying expert, that I am talking about the person who is observing it.
Yes, you can say that way. Observing in the image processing domain.
There is one expert who is the real expert of agriculture.
Yes,
He says
yes,
that this is
sure.
this category. Now we are correlating the same thing with the image processing results.
Exactly.
So now this is an expert or after his own observation that now okay, now this is, and he also says yes, this comes under this categories. Now we can say okay, these are the parameter for this,
Yes.
and statistics says that this is there.
Exactly. The two experts have to be in phase.
Yes.
There are a lot of problems which you while studying the one aspect you are not aware of them. I think some of these are now coming up. Could you imagine there is a lot of human element in it. We are trying to replicate a human expert within the machine.
Is it published somewhere? This
Yes,
whole detail?
this is published in international conference on AI which was held in Pune. They have made a if you search for net you will find this paper. If you search for net the classification of the paper has been done electronically, document. So, if you search for my name you will find this paper, full detail will be there. So, the idea is
With I, but I don't know what is V.
it is I think we have done actually I. I think in here we have put V because initial work was done with V.
V means
V is they are calling it value.
value.
MATLAB declares it as another model which they have not shown. They are saying HSI is the publicly known model. So, we have chosen HSI and we are
Similar to I.
it is similar to I do not know what difference they maintain. As you saw we were doing 1/3 of RGB. So, it is a simple calculation, sometimes they use maximum of RGB. So, I do not know whether they are using maximum or average. So, in our calculation whatever again that is where the training matters. If you have chosen a particular model, stick to it. You can't have a MATLAB feasibility study and then apply somewhere else with some other model, isn't it. So, these values are to be strictly maintained. So, though they can be statistically observed, these were done initially by personal observation, setting some rules, and then also now we have taken all the statistical analysis and we are thinking of a fuzzy model to that as well. But as such, to recall this point, This at this juncture it is actually pixel level classification. It is not actually whole grain level classification.
Yes, resolution dependent of the scanner.
No, 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 you are not getting. My point is, when I say pixel level means we are calling a grain has 100 pixel in. Suppose this whole mouse is replicating a grain. There is some redness here. Now we are calling this pixel is red, this pixel is chalky, this pixel is say discolored, this pixel is sound. We have a report of say there are about 300 pixels in a grain. Actually this is 50 by 50 kind of image in general for a grain, in which the grain pixels are somewhere 50 to 60%.
The moment it is pixel based, it automatically depends on the resolution of the scanner also.
Yes, yes, that 300, that resolution has been fixed.
More the resolution
Yes,
increases,
yes.
more efficiency
Yeah,
will come out of this.
Yeah,
More
that
bits
is.
will be there.
No, it is not that more is better always. The more is not that better afterwards. This is after you find 300,
Somewhere it
the
will
600 is not.
Somewhere it will converge.
Yeah.
definitely. So
No, it 300 is something we found somewhere, but we have also tried 600. The pixel level classification, yes, will be what we are talking about yet. At the moment, it is that pixel which we have chosen as per resolution. So that effect is there, and the classification at the moment is pixel level. What I am trying to say, it is not grain. Grain has all the elements in it. A grain may have some percentage of red, some percentage of discolorness, some percentage of chalkiness, some percentage of soundness, and some damage also. That is what we are trying to say. But each pixel is separately classified. Say there is a black spot here. So that pixel is declared as black, but other pixels are okay. So we know that okay, 1 out of 100 is black. So 1% is black, or 1% of say red grain is red. Now what do you call it? That we take as sample. The sample report says this has been declared say non-red, but the moment it is more than 1%, then the grain has been classified as say red. So we have seen that, and then it also competes with discolorness. Now when there is a discolored grain which has also similar values of say HSI. So as you can see, discolor has a broader H value, and S values are again different, 0.5 to 0.15 to 0.34. These are the values you can say hypothetically or actually by range analysis have been fixed. So some of them are overlapping, but on the whole a particular class cannot be overlapping with the other. So as these ranges, like for example damaged have 0 to 30 degree of H, also 330 to 360 degree, that is of course obvious. So like that we have the whole range analysis, which gives us pixel wise classification. At this juncture neither neural network has been used nor any other rule based has been used, you can say, as the first step to classify them as pixel level. So in a way, the moment it lies in this range, we say this pixel is red, then we count them, we count their score. It is like the grain has found red percentage marks, discolored percentage score, chalky score, sound score, and damaged score. So it has 5 say subjects in which a grain has appeared for examination, and there are 5 say percentages available. Now it is something like somebody has scored 80% in physics, 20% in chemistry, 60% in maths or something like that. What will you do? Oh, what is that? He has scored only 20% in chemistry. Whether to allow in IIT to get clearance or not, it is that kind of problem now we are facing. So we are trying to say that this is the level of range analysis. Now this gives the overall kind of rules combined with geometric features. This is the overall grain classification. Now you can see the rules wise you cannot put many. You will see for admixture we have taken only length and breadth and ignored all the parameters, because a human being in observation in rule based generation cannot find easy to generate rules. He cannot handle many dimensions actually. He will say okay, but length is in this range and breadth in this range. Even if you ask the expert, he may not be able to tell you more than 2 parameters in a rule. This is something a general problem with rule based. A human being will not be able to handle many dimensions. That is where the neural network approach can help. So at this juncture we have used neural network as well. So, the results of neural network are encouraging rather than the rule based. These were done as a MTech thesis program in the beginning. So, these rules are given for that purpose. So, you can see red is compared with red percentage as just anything above 0.75%, and it has to be compared with 4 times the 4 times redness is compared with discolored percentage. So, even a small percentage of redness has to be taken seriously, while equally seriously is 4 times of that in case of discoloredness. So, like that with some indications you can make a sense as to what we mean by sound, what we mean by inorganic. In fact, you find at the end of it inorganic has no parameters in it. Could you see that? That means, if nothing is found, let us call it inorganic. The last rule has no condition. That means, in a sequenced manner we have applied the rules. And then comes the results of this rule base. You can find that the results are not very highly encouraging, or some percentages are very low, because of limited analysis. This was a sort of results at the early level of an MTech student. So, we have not followed this approach now, we are using neural network approach. So, this is just to give you the first observation, manual observation could give some level of sounds were okay, 88, 86 kind of percentage. So, this shows the grains and each number of grains and classify. And then this shows how rule based could achieve some level of acceptance. Most of the time they are okay for the good grains, but they are difficult, the classification quality accuracy is poorer as the number of grains available with us were small. If you give 10 grains out of 7,000, 8,000 grains of red, how many times I see it, even more seeing is not so good. So, the rules could not be improved for, say, some of them are to be used for training, some of them are used for testing. So, training and testing put together will not generate, say we had 5764 kernels. Kernels are the number of grains, the term used is for grains. So, this is the accuracy for rule base, and I do not know if you can see this results. This is sort of what we call cross validation in the form of confusion matrix. This is neural network training. The upper table gives confusion matrix for training, the below the similar model gives the testing. So, 80% of the samples are used for training, and the training results here indicate that admixture had 71% training result, big broken had 97%, say chalky had 83%, sound grains had 98%, discolored has 83%. Like that, diagonally if you see, you can see the confusion matrix. That means, these are the correct percentages and other percentages are distributed in other classes. So, there is some confusion by the neural network, and the bottom one indicates the actual percentage, you can say, while testing. So, you can find that big broken has 91% or sound grains has 97%, but some of them gets reduced in terms of percentage. That means, they were good in training, but not so good in testing, because we had very small number of grains. What we found was, if we had more number of grains available, even the 7,000 number of grains were available, but most of them were good grains. So, we could train the system for good grains, broken ones and all that, but for other refractions which are indicated as classes requirement, they were less in percentage. And this shows the same diagram showing comparing, you see the training and validation for inorganic, very large difference. For training it was showing 100%, and for validation it is very low. That means, this is not accurate, not reliable kind of result. It is not a validation of result. That means, for inorganic we can't say much about the neural network. Neural network has not understood well, say, the training of inorganic ones. Similarly, wherever there is a difference between training and testing, that means the particular class has not been absorbed well by the neural network. That is the idea.
What exactly is done using neural network?
Neural network takes all the samples and the labeling is done by us. We have 100% samples marked properly as per the experts. We have all the parameters, 13 parameters. The training has been done on minimum attributes. In this case, sorry, these were the attributes used, what were used in the rule base. So, this is to match the rule base. you will find another neural network which use all the 13 parameters. This did not use 13 parameters. So, since the rule base does not use all the parameters, we try to match the same parameters used for rule base as well as neural network. So, this compares 1 to 1, as here the difference of training and validation I was mentioning. So, your point was how the training was done?
Why you have used neural network? What actually
Neural network is something that you can assume the training can be done. Who will system cannot do otherwise. The
I was
approach.
thinking that the neural network you are using for probabilistic
No.
classification or something.
It is classification.
Whether, rice
It is classified.
is good or not.
No, not just good or bad. We have 10 classes of these. Neural network can generate 10 classes also. Good or bad is just 1 or 2 classes, isn't it? It's a binarization kind of
Here
thing.
already they have done for 10 classes.
This is for 10 classes, not just. That's where we were finding difficulty of some of the classes. Just because we did not get enough number of samples. Finally, I was mentioning you, ultimately the whole project results depend on the availability of data and not availability of coding, I would say, or anything. So, if you have data, you have a treasure with you. If you do not have data, no matter what you do, you are not going to get anything, because you have nothing to see. So, the data shows us what is the accuracy, what is the result, what was the overall capability of the potential or the potential of the algorithm, isn't it? So, the code has to marry the data, no way. Other than that, you keep the code with you, nothing will come, because in this case Markford data was there. To some extent we had some data. So, some encouraging results have been obtained, but if you, as in some cases the number is still less, the availability is poor. So, we could not get good results. Now, it is all 13 attributes, same thing with larger number of attributes, considering all 8 plus 5 13 attributes, the results are improved, and still inorganic remains poorer, say by 8% again. While training it shows 80% training, because the number is less. Actually, there are, say, I do not know if there are 16 grains. Now, 16 grain 80% means 12 or 13 grains were used in training. The neural net learned training on only 13 grains, and then try to test the rest 3 grains. That is where you will find, if it finds one of them right or 2, I do not know how many of them. So, or few, I do not know whether 16 were there or not, but very small percentage has been shown here. But the other ones are okay. As far as sound is concerned, 95%, 97%. Basically, the good grains are classified appropriately. That is what we could see by the availability of this approach. Now, as you can see there, the red and green, red and blue kind of training and validation ratio indicates the overall what could be done appropriately. If there are differences in the two, that means that particular class is not well recognized. Now, even if you see red, damaged, inorganic, because the number was less, we did not find at the moment neural network fully trained. You said why it is used. We are using neural network as a matching expert within the system. So, it is an element now which gets integrated to the system. Once it has learned these rice grains classification, you give us a new sample, it will generate the report. Basically, it is an examiner now. Now, of course, I have already almost compared the two, and as he mentioned, the detailed comparison is available in the paper that we had published, presented in December 2007, and this just compares quantitatively what has gone wrong, what is better in neural network in compared to rule based approach, and overall comparison where in say less number of attributes and full number of attributes, what results could be obtained. This is of course not image processing details, and further I can say now that we discussed histograms. Now, you never knew that we could have parametric histogram. We do not do image histograms only, we do now it is a histogram for length of all grains, where the population is available on the x axis and the length is available on the y axis. In fact, the project allows any 2 parameters or 3 parameters as part of the report. You can generate reports. Again, already discussed the overall basically societal impact is that you can have total objectivity, transparency, reliability, 24/7 kind of behavior. You do not need to look for a person who will do this job, otherwise you have to submit a sample to the laboratory and then they will do the job. So, it is generally a half an hour to 1 hour kind of job by 2 or 3 people who will do this test and give a report. And this system can do in few minutes, and also maybe on an online kind of system where the milling process can be, say, on a site. You can, if you have an internet connection, have a scanner with you. Of course, this software can also be used by the computer there itself as a desktop version. What we were suggesting that if the rules are changing in the country sometimes, so they say allowed percentage this year to the farmers is say 10% of chalkiness allowed, or some other percentage of reflection allowed. So, that way if you want to change the reports by way of prevailing rules, the centralization can be done, or you can say manipulation of the reporting cannot be done if you use a central server. Otherwise, technically you can use your own desktop, or technically you can use web service, either way. Okay, that was about the case study. I know some of the details were of your interest, some of them were beyond, but it was almost necessary to give you the overall necessity of matching with the reality, facing the reality,